Anyway, so earlier on, we talked about Friedel oscillations, sometimes also called RKKY oscillations. And so these first few slides are meant to illustrate that effect. So remember, Friedel oscillations arose in the context of screening. And we asked the question, you put a test charge inside a metal, which we modeled by a simple Gilliault model. And then we calculated the response of a metal by calculating the dielectric function. And in Thomas Fermi approximation, we found a simple decay, exponential decay of the screening charge. However, in a Linard, more complete Linard approximation, we found that there's a component which actually oscillates in space. And this is something that is actually seen in many different experiments. So this is perhaps the most spectacular demonstration of that. So what you see here is a surface of crystalline copper studied by scanning tunneling microscopy. And this is a technique that is sensitive to the local density of states of a metal. Basically, it's a wave function of a state, or amplitude of the wave function of the state that is closest to the Fermi energy that is shown here. And these are terraces. Basically, this step is just one atom layer thick. And what you see is that both these edges produce these ripples in the wave function, which is the RKKY type interaction. But also, you have impurities on the surface, which are typically some foreign atoms that when you prepare your sample, there's always some impurities that contaminate your surface. And generally, these are unknown, but one can investigate what those are. But nevertheless, you can see that each of them is surrounded by a ring of these oscillations. And these can be directly attributed to these Friedel-like oscillations. So this is one spectacular image. One can do more things. So this is, again, a flat portion of a copper surface. And these are, again, some unknown defects that produce these ripples at 2 kF. Just let me emphasize that this is all false color, right? It's not like we're seeing it in color. What's being imaged is local density of states, and it's just enhanced and photoshopped to make appealing images. This is a cool one. So this demonstrates a more advanced technology. This is iron atoms on the surface of copper. And they exploit here a technique in which this STM, which is basically atomically sharp tip that you can move with atomic precision. And you can also use this tip to shove around these individual atoms and form patterns. So this is something written, I think, in Japanese. I cannot read it, but if any of you can read it, maybe you can tell me what it says. But this demonstrates, well, basically, this is the smallest letters that you can write, right? Because these are individual atoms, and you cannot write anything smaller, or at least I don't know how would you go about that. Okay, so that much about Friedel oscillations and STM. Here's some pictures of related to what we discussed yesterday, namely lattice vibrations, phonons. So just a few images here, starting up here. This is the dispersion of one-dimensional chain of atoms, just like we discussed yesterday. But this is a diatomic chain. Namely, you have two atoms with masses m1 and m2. And you can see that you get two branches of dispersion, acoustic and optical phonon branch. And these other pictures here are meant to illustrate that this is something that is actually observed in experiment as well. So this, for instance, is a phonon frequency spectrum of, I think, germanium in this case. So this is crystalline germanium at 80 Kelvin. And you can see a similar type of dispersion. This is a three-dimensional material, of course. And you see you see acoustic branches, which have linear dispersion at low momenta. And there's actually three of them. There's one, what they call longitudinal branch, where atoms oscillate longitudinally, meaning in the same direction as the wave is propagating, like sound waves in the air. And there are two transverse branches, which you can see just one because they are degenerate. But anyway, you expect three, because there's three independent directions of oscillation. You expect three branches that are acoustic, and then there are some optical branches. And the spectrum here, which is measured, looks very much like what you get there, at least qualitatively. There's another experimental result here. This is potassium bromide. And again, you see two acoustic branches, two optical branches. The coverage here is kind of spotty, but I'm showing this for historical reasons. This is one of the first such images ever obtained. And this is done by Bertrand Brockhaus. He's one of the few physicists of Canadian physicists who got Nobel Prize, and he got it for basically inventing this technique of triple-axis neutron spectroscopy that's now used universally for these types of experiments. And he did much of his work, well, he was based at McMaster University, and much of the work was done up at Chalk River, where they have a reactor that produces neutrons in these studies. So this is obtained by the same technique some years ago, so you can see that they can do continuous lines. Initially, they just did some points, but the technique was invented right here. And unfortunately, Brockhaus now passed away, so you cannot go talking to him, but he was a very brilliant physicist. So here's a kind of more schematic picture. What one does for three-dimensional crystals. Of course, in three-dimensional crystal, momenta are defined in a three-dimensional Brillouin zone. So this is a three-dimensional Brillouin zone for FCC lattice structure. Many simple metals crystallize in FCC face-centered cubic structure, for instance, lead, but also aluminum and others. And what you do in that case, you want to depict, say, phonon dispersion, but there's just too much information there, because for every momentum in this three-dimensional Brillouin zone, you have some frequency, right? So how do you present that in some intelligible manner? And the way this is typically done is that you select some path in the Brillouin zone that connects high symmetry points. Typically, the center of the Brillouin zone is called by capital gamma, and then you select a path that goes from the center, say, to the edge, then to the vertex, another point, and then back to the center of the Brillouin zone. And you plot the dispersion along those lines. So this is from gamma to q to x to w to x, k, q, and back to gamma. So that's a path shown there. And along that path, you plot the dispersion. And again, this is dispersion, phonon dispersion for lead, again, obtained by Brockhaus back in 1962. And what you see here, the black points here are the experimental results, whereas the white lines are the theoretical calculation along the lines of what we did yesterday, but of course, somewhat more sophisticated. And you can see that for a simple metal, the agreement is almost perfect. It would be suspicious if it was any better than this. Okay, another technologically important material, silicon, which crystallizes in the so-called diamond lattice. This is FCC structure with a two-point basis. And here you see a slightly more complicated spectrum, because it's a lattice with two-point basis. You expect to have both acoustic and optical modes. And indeed, what you see here, the points are the measured spectra by neutron scattering, and the black lines are the spectra predicted from a theoretical calculation. And again, you see this agrees reasonably well. Finally, I have a few pictures here related to the specific heat that we also calculated yesterday. And what's shown here is measured specific heat for various crystalline materials: aluminum, calcium fluoride, copper, potassium chloride, sodium chloride. So this includes some ionic insulators as well as metals. And the point of this picture is to show that when you scale them by the Debye temperature theta, those measured specific heats, they all collapse on this one universal curve that looks precisely like you would expect from this Debye approximation that we discussed last time. The limiting line here is the Dulong-Petit law, right? So if you were to calculate these spectra classically, then you would just find this straight line. And especially here at low temperature, you would find a huge discrepancy between your prediction and experimental result. Here, when you treat these degrees of freedom properly quantum mechanically, you find that there is actually a good agreement. Question?
Yeah, that's really an amazing agreement with this theory, the theory of this theory.
Yes.
Did Debye receive the Nobel Prize for this?
I don't think Debye received the Nobel Prize for that, or at least, well, I'm not aware of that. He did this work. I checked yesterday. It was 1912 when he published his paper on specific heat, and yeah, these. Well, yeah, he certainly. If he didn't get one, he certainly deserved one, because this at that point that was a long-standing big problem for classical physics, and he resolved it by this application of quantum mechanics. Yes.
In the previous slide, you said the fact that we had a basis on our lattice, you said that would mean we expect optical spectra too.
Yes.
Why is that?
Can you repeat the question? So why would you expect, or?
Why did we, it sounded like you said that we expected an optical spectrum because we had a basis on our lattice.
Yes.
Why is that?
So that's because, yeah, I tried to mention or explain that quickly yesterday. So when you have more than one type of a lattice, one type of an atom in your lattice, then you have more modes that are available. And mathematically, this comes because the matrix that you diagonalize has larger size. So generally, in a lattice n-point basis, you still have just one acoustic mode, but you have n-1 optical mode. So if you have a 2-point basis, you expect to have one acoustic mode and one optical mode. When you have more atoms in a unit cell, then you have more optical modes, whereas there's always just one acoustic mode. And yeah, any other questions? Yes.
Yeah. Also, in the previous slide, there was some degeneracy breaking in the transverse modes. Yeah. Why is that? This degeneracy breaking between X and gamma. Acoustic modes.
Here.
Yeah.
Yeah. So that all depends on crystal symmetries. So along this line, apparently these two transverse modes are degenerate, but and there must be some symmetry that protects that degeneracy, and I don't really remember exactly what that symmetry is, but along this line, that symmetry apparently is broken, so those modes are no longer degenerate. Yeah. Any other questions? Yes.
There's also interesting thing between X and U. The acoustic and optical modes actually meet, and then they split, even not on the boundary on U, but they split even before.
You mean this region here?
Yeah.
Yeah. So yeah, if you look here, this is more of a canonical. If you look at this region, that would be more of a canonical behavior of acoustic and optical modes. Here, they actually meet, and once again, one would have to analyze the fine details. There is apparently along this line there is another symmetry that forces these modes to be degenerate, and I don't think there is a general rule that tells you how this works out. One has to go, and study the particular lattice structure in detail. This actually looks more like an accidental degeneracy because you see that the two lines actually split before they hit the boundary of the Brillouin zone, right? So if this was a symmetry-protected degeneracy, one would expect it to hold everywhere along that line, but like also here. So perhaps there is a symmetry-protected degeneracy at this point, and as you move here, there is some perturbation that splits that degeneracy, but it's very small. That can also happen. And then you have what we call accidental degeneracy, where it's not protected by symmetry, but the perturbation is numerically small, so it looks like it's degenerate. Okay, so finally, so this is a kind of overall agreement between Debye theory and experiment for a number of different compounds. There's interesting things that one can learn by zooming in on the low temperature behavior and analyzing that in more detail. And this is what is shown here in this graph. So here is a low temperature part of heat capacity or specific heat for potassium crystal. And the way this is plotted as a function of t squared. And what the quantity that is plotted is the measured specific heat divided by temperature. And this is a very useful way of plotting that if you want to disentangle the phonon and electron contribution. So phonon contribution goes as t cubed, as we discussed. So when you divide it by t and plot it as t squared, then phonon contribution would show as a straight line. However, the electronic contribution goes like just temperature. It's linearly proportional to temperature, so it would show as just an intercept in this plot. Namely, you expect for a metal for the total electron and phonon heat capacity to go as a constant plus a coefficient times t squared. And so you can see, first of all, that in potassium and again many other simple metals, this is satisfied to good accuracy. This is beautifully linear data. Plus, second, you can read off the actual amount or value of phonon heat capacity, the prefactor that gives you, say, the Debye temperature from this coefficient here. And you can also read off the electron contribution just from this intercept, which is this coefficient gamma. So often in the literature, you would find these types of plots that help you disentangle the two contributions of to heat capacity from electrons and phonons. Any other questions? Okay, so to the people in the booth, can you please turn this off? And if someone could undim the lights, then I could go. Thank you. So that's the end of our multimedia presentation. I go back to the blackboard. And the topic today is Magnons, or quanta of magnetic fluctuations, which is another example of emergent bosonic particles in solids. So magnons, as you can hear from the word itself, are part of magnetism. And magnetism is a huge field in condensed matter. It's a field that is both intellectually deep and technologically very important. All your high-capacity hard drives are based on magnetic materials. Every electric motor has a high-strength magnet in it, and there's other important technological applications of magnetic materials. We will just have time to scratch the surface of this vast field. I will devote just one lecture today to Magnons and basic theory of magnetism. And what we will discuss is one of the most ubiquitous models that is used to describe magnetic solids, which is the so-called Heisenberg Hamiltonian. And let me first write down the Heisenberg Hamiltonian for you, and then I will comment on where it comes from and so on. So this is the famous Heisenberg model, and it describes a solid in which we imagine we have individual ions forming some crystalline lattice, and these ions have magnetic moments that we call SI, SJ. Okay. Now, there's, yes, question.
Magnon and a spin wave, or the same thing?
They are the same thing. Yeah. Magnon, sometimes also called spin. So there's lots of physics that goes into understanding where exactly this comes from, but at its very simplest, you can just start from atomic physics. And you know that whenever you have an atom whose shell is not closed, then the ground state of that atom, according to Hund's rules, is such that its magnetic moment is maximal. The largest the magnetic moment you can construct, that's going to be the ground state of that atom. And that's the effect of interactions that are described by these Hund's rules that are used in quantum chemistry all the time. So it is perhaps not surprising that when you put such atoms together and they form a solid, often they will retain either all or some of its magnetic moments. And then the simplest model, really, that you can write down, and this dates back to early days of quantum mechanics, to Heisenberg himself, is a model like this, where the magnetic moments on sites I and J simply, and these are typically taken to be nearest neighbor sites in some crystalline lattice. The simplest scalar that you can form out of two vectors is their inner product, right? So energy has to be a scalar, and then there is some energy scale associated with it. And then the second term describes the effect of external magnetic field. So this is external. And 2 mu naught here, or just mu naught, is G over 2 times Bohr magneton. G is the Landé G factor, which basically tells you how much this magnetic moment interacts with the magnetic field. But basically, the second term just tells you it's the Zeeman effect, right? When you apply magnetic field to a magnetic moment, it wants to be aligned with that magnetic field. So it's interaction between neighboring magnetic moments and alignment of magnetic moments with external magnetic field. Okay. Now, there can be there are two broad cases or broad classes of systems depending on the sign of this exchange coupling J. So J is also called exchange coupling. And that has to do with the fact that in most magnets, it arises from the so-called exchange mechanism. And I will not go into what it exactly means. Basically, it has to do with electrons hopping between these sites and mediating this magnetic interaction. And there are two important cases, namely J can be greater than 0, in which case you expect that the ground state of the system will be such that all these spins are aligned, right? Because when they are aligned, then their scalar product is positive. And with J positive, this minus sign favors such alignment. So this is also called ferromagnetic case. And symbolically, you expect all the spins in the ground state to be aligned. And the opposite case is J less than 0, which is also called anti-ferromagnetic case, in which you expect the neighboring spins to be anti-aligned, because when J is negative, you want this inner product to also be negative and maximal. And that arises when the two neighboring spins are anti-aligned, at least classically. That's what you would expect. So it turns out that in nature, there's many more antiferromagnets than ferromagnets. And it's kind of interesting because ferromagnetism actually has been known to people since antiquity. Even people like Aristotle and these guys, they knew about ferromagnets and they knew about compass and things like this, just because ferromagnetism is relatively easy to test in a lab. Two pieces of iron ore often attract or repel one another depending on how you align them. However, antiferromagnetism has not been discovered until basically people perfected the technique of neutron scattering. And that was fairly recently. And then we find that many compounds that we did not really suspect, like metallic chromium that's been used for many years, it's an antiferromagnet, but antiferromagnetic metal. We didn't know that. So ferromagnetism is kind of well known, but antiferromagnetism is even more common, although much more difficult to detect. So what we'll do, we will discuss today the case of ferromagnetic Heisenberg model. We will study this Hamiltonian and its excitations, which are called Magnons or spin waves. And then in the next tutorial, you will actually do the same for the antiferromagnetic Heisenberg model with a negative J. Or is it in the homework? Sorry, yeah. Yes, you will get to kind of repeat this analysis in the next assignment. So let's discuss J greater than 0 case, namely ferromagnetic. And in this case, the ground state is just a ferromagnet. Namely, all the spins in the lattice are aligned. If you just have the first term, then there is an SU2 continuous group of transformations that you can apply, and all those states are equally valid ground states. So the ground state is hugely degenerate, if you wish. However, you can break that degeneracy by applying even very weak external field, and then all the magnetic moments will align in the ground state with that magnetic field. It is easy to show that a ferromagnetic state is an exact ground state of this Hamiltonian. In the other case, in the antiferromagnet, it turns out this naive antiferromagnetic state is not an exact ground state of that Hamiltonian, just because of the quantum mechanical effects. But in the ferromagnet, this actually is the ground state. So what we'll be interested in is understanding what happens when, for instance, you raise temperature a little bit. What are the excitations above this ground state, and how does the state behave when you do that? Okay, so before I go on, let me just remind you of some properties of the spin operators. So spin operators satisfy the usual SU2 algebra, and it looks like this. Okay, so I'm using a notation in which the lower index labels the site on which this spin sits, and the upper index labels the component of the spin. So alpha, beta, gamma stand for x, y, and z component, or in this notation, 1, 2, or 3 component. And this just compactly expresses the fact that a commutator of 2 different spins on the same site gives you I times the third component, right? So for instance, Sx, Sy would give you I, Sz, right? And vice versa. This delta Ij tells you that if the 2 spins refer to different sites, then the right-hand side is just 0, okay? And this epsilon is the usual Levi-Civita totally antisymmetric tensor. Another important identity for spin operators is the following: Si dotted into Si is S times S plus 1, where this S is the eigenvalue of the S squared operator, namely S squared I acting on a spin state, let's call it S, is S times S plus 1 acting on that same state, whereas SZI acting on a state with spin S is S times S. Okay, so once again, as I mentioned, the ground state, and you can check this, it's very easy to check, is just when J is greater than 0 of this Hamiltonian is just a perfect ferromagnet. However, the excited states are not as easy to understand, and people who first understood how to deal with them were Holstein and Primakoff, and they developed a transformation that we will now discuss. So excited states Holstein and Primakoff this has been done back in 1940, so we're still in the ancient days, not quite 100 years ago, but almost. So what Holstein and Primakoff noticed is that, you see, so the reason why this problem is somewhat difficult to solve is because the three components of spin, Sx, Sy, and Sz, are really not independent, right? They are connected either through this commutation relation, or they are, you can view this operator identity as a constraint, right? When you specify two of these components, the third one is already given by this constraint. And that's why solving this Hamiltonian for all the excitations is somewhat complicated. So what they invented is a transformation to express spin operators in terms of bosons. Spins into bosons. And this is an exact transformation. It's canonical, namely you satisfy all the commutation rules. But in its exact form, you cannot really solve the bosonic problem exactly either. So there's some approximations that one has to take. However, these are very good approximations, especially when you're at very low temperatures, so that there's only few excitations above the ground state. So Holstein-Primakoff transformation looks like this. First of all, you write on any given site S plus, which is Sjx plus I Sjy. So this is like a spin raising operator that raises the Sz value of spin on site j by 1 unit. And one can write it in terms of bosonic operators like this. 2s one minus a dagger j, aj, divided by 2s to 1/2 times aj. And similarly for the lowering operator, Sj is Sxj minus Isyj is 2s times 1 minus a dagger j, aj over 2s times a dagger j. And there's 1/2 here. Now, how would they come up with this kind of weird nonlinear transformation? The motivation is as follows. You know that for spin s, you have 2s plus 1 different values of Sz, right? Whereas for bosons, for any bosonic operator, the number of bosons on each site can be arbitrary, right? So somehow you have to, when you have a mapping from spin operators to bosons, you have to take care of this disparity in the Hilbert space. And this is exactly what this prefactor does. Notice that this is simply n of j, just a number operator for these bosons. And when n of j becomes equal to 2s, then this prefactor goes to 0. In other words, when you try to raise, so you start from some spin state and then you keep raising by applying repeatedly this operator, at some point you come to this state where you can raise no more because you reach the maximal spin. And indeed, in bosonic language, this guy just becomes 0, so that restricts the Hilbert space. Yes?
Why are you associating an annihilation operator with SI? Sorry, like SI plus. It's like you're raising spin, but you're annihilating.
Yeah, so that's an unfortunate thing. I don't know why Holstein and Primakoff wrote it right like that. It would be more natural to put a dagger here and not a dagger there. It works either way. This is somewhat counterintuitive. Yeah. But I'm just following the standard text here, so that's how they figured it out. Yeah. So these A operators are standard bosonic operators, and they satisfy AJ, A dagger K is simply delta JK. And so what we still need is the expression for SZ component of spin. And one can get it either from here or from there. It's actually easier to get it from this expression. So let me just write this expression as follows. I express S Z. So let me focus on a single site, and therefore I don't have to worry about these indices J, and let me lower the index Z so that I can easily write SZ squared. And then from that equation, that clearly is equal to S times S plus 1 minus S x squared minus sy squared, right? I'm just solving that equation for SC. And this can be written as S times S plus 1 minus 1/2 S plus S minus plus S minus S plus. And you can check that when you plug in these S pluses, minuses, you get back this. And now what I can do, I can just plug in these expressions of Holstein-Primakoff here. And the nice thing is that these square roots that I have, since I have a bilinear here, they cancel out. I will just have this without a square root. Yes, question?
I think the A dagger is on the left and
Yeah, it was before the square root in one of these formulas. Operator A must
yes.
be before.
otherwise the projectiles fall.
Yeah, that's true. Okay, sorry about that. Yeah, this A dagger J has to be here. Yeah, sorry about that. Yes, good point. Anyway, so now I just substitute, and since these square roots disappear, I can actually work this out easily. And when the dust settles, I get the following expression for SZ squared. It's S minus A dagger A squared. And from this, I conclude that SZJ is S minus NJ. Okay. Now, once again, what one still needs to check is that, as defined, these operators S plus, S minus, and SZ properly satisfy this commutation algebra. This is somewhat messy to demonstrate because of these square roots. Basically, the way it's done, you either use some trickery or you Taylor expand these in powers of these n's and then resum. I will not go through that. I will just assure you that indeed this transformation is canonical. These commutation relations are satisfied. And if anybody wants to see, you can go back to this 1940 paper where there is an appendix where they actually work this out in detail. Okay, any more questions about this? So now, what we want to do, we want to express our Heisenberg Hamiltonian, that's written here, in terms of these bosonic operators, and employ some suitable approximation so that we can solve that Hamiltonian. Okay, and let's the suitable approximation is the following. Let me first motivate this physically. So this is the simplest thing to consider physically. As you know, this SZ has eigenvalues that range from minus S to S. Okay, so SZ eigenvalues, they range between minus S to S, just the basic lore of spins. So here we have plus S, here we have minus S, and then the eigenvalues go between them. And this corresponds to the number operator that goes from, at this point, Nj is, what is it? It's minus 2s, and at this point, Nj is 0, right? Plus 2s, yes. So, yeah. So basically what you're doing here, so it's advantageous to think of this ferromagnetic state as being up, so it's in this state, right? It's all the spins are maximally aligned with whatever magnetic field you have. And then this Nj is 0 in that ground state, meaning you have no bosons in the system. It's the ground state, which is a boson vacuum. And then you can imagine that excitations of this system correspond to canting these ferromagnetic spins a little bit, which means you go from this state down to one of these states with a smaller projection of S onto the z-axis. And that corresponds to Nj equals 1, Nj equals 2, and so on. So you can identify these bosons as their presence as elementary excitations of the system. So these guys can be thought of as excitations of the system, and we call them Magnons. Because they are quantized, and they represent quanta of this magnetic fluctuation. And Aj and A dagger J are annihilation and creation operators of these Magnons. So the approximation that we need to make to make progress on this Hamiltonian is that of large spin S. We take this S to be much larger than 1, and we study. So this is first point, and the second point is study low-lying excitations, namely those for which Nj is much smaller than this S. Okay? So, I don't know, when this S is 10, say, we will restrict our attention to excited states in which n is 1, at most 2 on any given site. Yes, question?
Is this got something to do with if you go over like the halfway point, then by adding bosons you're kind of decreasing the energy because you've got like 2 ground states on the group?
Well, technically, this has to do with the fact that what we want to do, we want to claim that this ratio here is much smaller compared to 1, and we want to expand these square roots in the powers of this small parameter and only retain the leading term. And in that case, we will see that the Hamiltonian that we have over there becomes just bilinear in these bosonic operators, and we can solve it by methods that we know how to perform. Okay. So under these conditions, we expand square roots and retain only dominant terms. Physically, this approximation simply means that, well, the transformation in that approximation is no longer canonical, and the mistake that you're making is that basically, if you only retain the leading term, you're able to excite an arbitrary number of these bosonic states. So, you can go below this minus S in principle, right? You can go to lower states, which in spin language, they don't really exist, right? But as long as we're in the limit where the nj is typically much smaller than s, we don't really worry about what's happening here because we don't really populate those states. Yes?
So the approximation is as much bigger than 1?
The approximation is nj much smaller than s. So this ratio here is much smaller than 1. Yeah.
And what does the first line say then?
Bullet pointer on A.
The first line says that we need the spin, total spin, to be much larger than 1.
It's a bullet point.
It's a bullet point. It's not A. That's just
Okay. This is just a bullet
Oh,
here. Yeah.
okay.
And yeah, because for instance, if this spin would be 1/2, right?
Yeah, sure.
Then we would never be able to have nj much smaller than 1/2 since nj is integer. Now, so this is the approximation that we're using. Nevertheless, people use this transformation even for spin 1/2, and it works surprisingly well. And why that is so, yeah, it's understood to some extent. But as many of these approximations, you push them as far as you can, and then at some point you find a contradiction. But anyway, question.
You mean a single spin half atom?
No, a system of a spin 1/2 atom.
Right, so you can still get large S situations, right?
No, but this S corresponds to a single spin.
Oh, a single spin.
Yeah, this S is just a single spin value, right? So we assume that we have a collection of atoms all with the same spin, right? And that spin can be 1/2, 1, 5/2, 7/2, whatever. Technically, we're assuming that this S is much larger than 1. But like I said, often people use this approximation even when this is not satisfied, and it has surprisingly good results. Anyway, so let's rewrite the Hamiltonian. So we expand. So let me write down this expansion, and then we rewrite the Hamiltonian. Basically, this expansion looks like this. S plus j is then approximately equal to square root of 2s. And we have aj minus nj over 2s times aj plus ... And similarly for s minus j. So this is the expansion in, and this should be 4 here, because when I take a derivative of a square root, I get another factor of 1/2. And similarly for s minus. And then I want to substitute that into my original Heisenberg Hamiltonian. So let's study the term si dot sj. Let's see how it works out. So first of all, I write it as sxi sxj plus syi syj plus szy szj, just from the definition of the inner product. And then I express these sx, sy in terms of s plus, s minus. So this is s plus I, s minus j, plus s minus I, s plus j, plus szy, szj. And now I substitute this, and I only retain the leading term, meaning this one. Okay? And this is justified by my assumption that nj is much smaller than s. So this ratio here is much smaller than 1, so I can neglect everything here when that's satisfying. So this is going to be approximately equal to, within this approximation, to s times a dagger I aj plus ai a dagger j. So this is these two guys. And then I get something from my sz components. And again, to that same leading order, I get s minus ni minus and j. Okay? And again, there would be higher order terms, but I'm neglecting them in this approximation. Now, the second term in my Hamiltonian, the Zeeman term, if I choose magnetic field along the z direction, or equivalently, whatever the direction of the field is, I say that I quantize my spin along that direction, then this term is, by definition, already bilinear in my operators, because Sz is just proportional to S minus Nj, so I don't have to approximate that at all. And I can now write the full Hamiltonian in this approximation, and it looks like this. Okay. Now, I introduced Z, which is a coordination number. And coordination number is simply defined as the number of nearest neighbors in a lattice. For instance, in a cubic lattice, Z would be 6 because you have 1 to the right, 1 to the left, 6 nearest neighbors, and so on. So these are just constant factors that come from, for instance, this term here and this term here. And all the operator content is in these H0 and H1. And H0 will contain terms bilinear in A dagger, and this will contain higher order terms, which we will neglect. Okay, so let me just write this H0, and this H0 is useful. It is useful to write it in the Fourier space. So for a translation invariant system, I write new operators, which are simply Fourier transforms of my A's. And in terms of these operators, H0 has the following form: minus J Z S sum over K gamma K BK B dagger K plus gamma minus K B dagger K BK minus 2 B dagger K BK. And then there is a term from the Zeeman effect, 2 mu naught B sum over K B dagger K BK. This gamma that I introduced here is defined as 1 over Z times sum over delta e to I k dot delta, and delta are the nearest neighbor vectors. For instance, delta would be x minus x, y minus y, z minus z multiplied by a naught, the lattice constant for cubic lattice. And some more complicated nearest neighbor vectors for more complicated lattice structures. So there's some intermediate steps that I skipped here, but we did this before, and I don't want to just redo things that we've done. Just imagine what we did. For instance, let's look at this term, right? We have AI, A dagger I, AJ, right? And we're summing over all I and j that are nearest neighbors in the lattice. We would express these two guys in terms of their Fourier transforms, right? We would invert this and express AJ in terms of BK. But of course, their positions differ. Xi and Xj differ exactly by the nearest neighbor vector, and that's where this gamma arises, right? And so here, when I take care of all those terms, I would get this gamma bk, b dagger k, and so on. The last term here arises from these ni and j's, because these guys are a dagger I, ai, right? So they are on the same site, and for that reason, there's no nearest neighbor vector involved, and that's why these terms here don't have any gamma in them. There's two of them, ni and j, and that's why I have a factor of 2. And similarly for this term that arises from my Zeeman term. So is this more or less clear to everybody? If you have kind of doubts in your mind, I urge you to just sit down and plug these b's, perform the summations, and see that you actually get that. It's about 2 or 3 lines of algebra. Okay, so now we can analyze this Hamiltonian. So if you look at this, these are just some constants, so we don't really care about them. We're neglecting this H1, which contains terms that would have higher numbers of these b's, products of 3, 4, and so on. These can be thought of as Magnon-Magnon interactions, and to leading order, we're neglecting them. So let's look at this Hamiltonian, and what can we learn from it? Okay. So let me note a few things. First of all, sum over k of gamma k is equal to 0, and one can check that. For any non-zero delta, this is true. This is just basic property of these exponentials. And second important property is that gamma k is equal to gamma minus k for lattices with inversion symmetry. Inversion symmetry means that for each nearest neighbor vector delta, there is an opposite nearest neighbor vector minus delta. So for instance, this cubic lattice has inversion symmetry because for vector x, there is a vector minus x, and so on and so forth. If you had, for instance, a triangular lattice, triangular lattice is okay, that has inversion symmetry. But the honeycomb lattice would not have an inversion symmetry. Honeycomb lattice looks like this. So this is not a Bravais lattice. It's a triangular lattice with a two-point basis, but nevertheless, the nearest neighbor vectors are these three, right? So for this one, there is nothing that is minus it. So this would be a lattice without inversion symmetry. And there's examples in 3D of lattices without inversion symmetry. But let's focus on those that have inversion symmetry, in which case the spectrum becomes quite simple. So in a lattice with inversion symmetry, we can write this H naught in a slightly simplified form. Basically, what happens is that this gamma minus k becomes gamma k, and we can just commute these two guys and put everything together. And the Hamiltonian, the part that contains operators, looks like this. We get 2jzs times 1 minus gamma of k plus 2 mu naught b dagger k bk. And now this looks like just a non-interacting gas of bosons with a dispersion that is given by this expression. In other words, we can write this as sum over k h bar omega k b dagger k bk, where this whole thing we call h bar omega k. Okay. So one can now, well, to analyze this further, one would have to assume some particular lattice and calculate these factors. And this would not be difficult to do for, say, a square lattice or FCC or what has you. But to get some universal properties, let's study the behavior of this system at long wavelengths, which we expect to be important at low energies. Meaning k goes to 0. And when k goes to 0, we can clearly expand this, these exponential factors to the leading order. And namely, what we want to expand is actually 1 minus gamma k. We want to expand that to leading order. And you can check that in the limit when k goes to 0, z times 1 minus gamma k can be approximated as 1/2 delta k dotted into delta squared plus some higher order terms, which we neglect. How that happens? Well, the leading term, when you expand this, is just a unity, but 1 over z times that unity precisely cancels this 1, so there will be no constant term. Then you will have a linear term in this expansion, but in a lattice with inversion symmetry, those also cancel, because for each delta you have an opposite vector minus delta, so to leading order they cancel. So the leading term that does not cancel out is the one where these guys are actually quadratic. And so under these conditions, h bar omega k goes like 2 mu naught b plus js sum over delta k dot delta squared. And for simple lattices, so for simple cubic BCC and FCC lattices, this guy just becomes some coefficient times k squared. You can see that for a simple square lattice, right? Because all these are just Cartesian coordinates. So k dot x would give you kx squared plus ky squared plus kz squared. This would just add up to k squared. And a similar thing happens for body-centered cubic and face-centered cubic lattice. And in these cases, you would find that this furthermore can be simplified to 2 mu naught B plus 2 Js times K squared. So basically, what you have here is a free boson gas. So the excitations of the Heisenberg model, ferromagnetic Heisenberg model, in the low energy approximation are basically described by this simple Hamiltonian, which describes a bunch of non-interacting bosons, also called Magnons, and they have a dispersion that is quadratic with some constant offset if you have applied magnetic field. Any questions about that? So let me write that down. And Magnons are non-interacting bosons with quadratic and when I say non-interacting, I mean in the approximation when we're neglecting the higher order terms, there are some effects that when you want to study them, you have to reconsider these terms that we just neglected. Okay, so let's now, since we've done this manipulation, let's now study this some physical consequences of these excitations. And one of the simplest things that you can measure is Magnon-specific heat. Right, just like from phonons in a magnetic material, these magnetic excitations, they contain some energy, and therefore they will contribute to the specific heat. And the calculation is very similar as for phonons. It's just that in phonons we had linear dispersion. Here we have quadratic dispersion, so there will be some differences. So let's do that relatively quickly. So let's take B equals 0. We apply 0 magnetic field, and in that case, h bar omega k can be written as d times k squared, where d is 2sj a squared. So I'm just restating this. I'm introducing this constant d so that I don't have to write these 5 symbols all the time. And we write the internal energy just as before as sum over k h bar omega k times the expectation value of nk, where this will be the Bose-Einstein distribution function. And I immediately rewrite this as an integral d3k over 2 pi cubed dk squared divided by e to beta dk squared minus 1. And the way to calculate these integrals, as usual, is to go to spherical coordinates and then do a substitution. So spherical coordinates and the substitution, where I define as x this term in the exponential beta dk squared. I do that substitution, and what I obtain is that the thermal energy is kBT to power 5/2 divided by 4 pi squared d to power 3/2. And then I have some integral 0 to some maximum cutoff, which would correspond to some Debye type cutoff for Magnons. And this is 3/4 here. So now, as you recall, to study the low temperature behavior in phonons, we were able to just send this xm to infinity. So for low t, we just send this xm to infinity, in which case this integral becomes a constant, and it can be expressed in some Riemann zeta functions and whatnot, which is not really important for us. But the important part is that the temperature dependence then just comes from this prefactor here. So the internal energy goes as t to power 5/2. And from this, we can read off the specific heat at constant volume is just du over dt in this limit of low temperature. When you evaluate this integral and put everything together, it becomes something like this. Again, to leading order, it's 0.113. That's just the value of this integral and all the pi's and everything. Kb times kBt divided by d to power 3/2. Okay, so the important information here is this power of 3/2, right? This is different from phonons. In phonons, we get power 3. So in principle, if you have a magnetic insulator, so that you'd expect that low temperature specific heat is contributed by ferromagnetic magnons, and of course you have some lattice vibrations, so you have ordinary phonon term. You can distinguish the two by just looking at the power that one has power 3, one has power 3/2. So you should be able to distinguish that in experiment. Yes?
Is there some way of like cutting off the distribution where you get more, you get like too many bosons? Because, you know, this distribution could go like, could have, sorry, like your boson distribution could give you, say, more bosons than you have allowed levels.
Yes, that's what I'm going to discuss next. Yeah. Any other questions about the specific heat? Okay, so let me, for better visibility, move to the other side. And let's move on to the last topic. So here's another quantity that one can actually measure experimentally and calculate theoretically, which is called magnetization reversal. So basically what one can easily do experimentally is to study the total magnetization of a sample as a function of temperature, right? And just as was mentioned now, in this picture where each of those bosons, when you excite it, corresponds to lowering the magnetization by 1 unit, you can presumably measure that experimentally and compare it to this theory. So magnetization, which is often denoted ms, is just 2 defined as 2 mu naught times sum over j s z j, right? And this is something that one can calculate from this theory. And when I substitute for sz from here, I do the Holstein-Primakoff transformation, then this becomes 2 mu naught and s minus some over j, expectation value of nj. Typically, what people define is actually, so I define this as a magnetization as temperature T. I'm evaluating this expectation value at some temperature T. And the quantity that people look at is the so-called magnetization reversal, which is just defined as the difference between magnetization at 0 minus magnetization at a given temperature. And this is nothing but this part here, right? So this is just 2 mu naught. And I can now write it in momentum space, k sum over nk. And this is basically the same quantity as the energy, except I don't have this multiplied by h bar omega k, right? We can calculate it by similar means. And let's do this. Let's evaluate this integral. So let's evaluate the integral corresponding to this quantity in arbitrary dimension now, because there's something interesting to be learned from this calculation that way. So I'm evaluating delta mt. And let's just forget about this prefactor. That's not so important. So let me just write this in dk 1 over e to beta dk squared minus 1. So I'm calculating this in arbitrary dimension, and all those factors of 2 pi squared or 2 pi to power d, they are just somewhere lumped into this constant of proportionality that is not important for these purposes. So let's evaluate this integral for arbitrary dimension. And the way to do this is, again, to go to d-dimensional spherical coordinates, because this integrand just depends on the magnitude of my k vector. And I can do this like so. I can do the volume element, and then the integrand is 0 to some k max dk k to d minus 1 over e to beta dk squared minus 1. This SD is just the surface of a unit d-dimensional sphere. Again, it's just some constant that I'm not really interested in, but it's non-zero. For instance, this would be 4 pi in 3 dimensions, 2 pi in 2 dimensions, and so on. But the point is I can now evaluate this integral, and I do that by exactly the same substitution, x equals beta dk squared. And I can evaluate this as follows. Okay. So this is the result. And there are a few things to note. So first of all, again, in the limit of low temperature, this x max goes to infinity. And this integral, because of the exponential in the denominator, is always well behaved for large x. So I can extend this x max to infinity at low temperatures. And then all the temperature dependence will come from here. And one thing, for instance, that I can study from this is I can find crude estimate for the phase transition temperature, right? You can imagine what happens. This magnetization starts as being large because all the spins point in the same direction at t equals 0. And then as I ramp up temperature, this starts growing, some spins start reversing, and at some point I go all the way to 0, right? So I can estimate the temperature. So as a function of t, this ms of t will go something like this, right? And I can estimate this Tc as a temperature at which ms Tc goes to 0. And I emphasize that this is a very crude estimate because, of course, at this point, I'm not really in the limit of validity of this approximation. Namely, this nj is now on the order of s. But nevertheless, this gives me some idea as to what the transition might be. And in a three-dimensional ferromagnet, actually, this works within factors of 2. This is a reasonable approximation. However, here's an interesting point. Interesting point comes and also I can say something about the low temperature behavior of this curve here, which will go as t to power d over 2, right? And again, this is something that can be tested experimentally, and in 3D, this works fine, okay? However, there's a bit of a surprise when you look at this integral here, right? This I declare to just be a constant and therefore not of much interest because I have neglected some prefactors already. But notice that this integral here for d less or equal than 2 is divergent at x goes to 0 bound, right? For instance, when d is equal to 2, this numerator is 1, and e to x minus 1 goes like x for small x. So this would be logarithmically divergent in 2 dimensions. In dimension less than 2, this divergence becomes even more severe because when d is less than 2, I will start getting some negative powers of this x. So this integral is even more divergent. And so I come to the conclusion that in dimensions 2 and below, at any finite temperature, this will, this is infinity, right? So this will immediately kill my magnetism in a sample, right? Below d equals 2 and d equals 2 included, Magnon fluctuations kill ferromagnetism at any non-zero temperature. Okay, and this is a kind of interesting result, which is in agreement with what is known as rigorous Mermin-Wagner theorem. The letter states that there can be no continuous symmetry breaking in dimensions less than 2 at non-zero temperature. If you analyze this expression more carefully, you would find that in 2 dimensions, at exactly t equals 0, the order is possible. So the system orders ferromagnetically at t equals 0. But as you ramp up temperature, even infinitesimally, these magnons just proliferate and kill this ferromagnetic order. In 1 dimension, this case is special because ferromagnet is an exact ground state of the Hamiltonian. But more generally, in a somewhat more complex models, you would find that in one dimension, even at t equals 0, such order is impossible. And that's the case, for instance, for the antiferromagnet. In the ferromagnet, there's an exception in 1D here, and the order would survive. But in a kind of more general model, Mermin-Wagner theorem would tell you, or its equivalent would tell you, that even in one dimension, you would not be able to sustain any long-range magnetic order. And this is a very general property of matter, that the lower the dimension, the less stable things are. For instance, you can actually do a similar analysis for phonons, right? And analyze the stability of lattices in various dimensions. And this is the last thing that I want to say. And you would find a very similar behavior. You would find that in 3D, everything is fine. Phonons just lead to some displacements of atoms, and there's some transition temperature at which your 3D crystal melts, and the rigidity, roughly speaking, looks like this. There will be some non-zero temperature. However, when you go to lower dimensions, you would find these infrared divergences in your integrals, which tell you that things are unstable, right? And indeed, it is known that in low dimensions, even translational long-range order crystals don't exist in one dimension. And one has to reconcile this with things like carbon nanotubes, which are long and basically one-dimensional, and two-dimensional graphene sheet doesn't also exist theoretically, but experimentally it's a perfectly fine material. So there's some profound issues there, but they're well understood. Basically, something that looks solid to you, like two-dimensional graphene sheet, may not have true long-range order, meaning when you go far enough between two atoms, you find that those positions are basically uncorrelated. But nevertheless, it has tensile strength. It exists as a material that you can use, but it's not really a crystal in that sense. It's not ordered in the conventional sense. Anyway, so this type of simple analysis for a ferromagnet shows this behavior in a simple context when one can actually compute things, and it's a very general phenomenon. That's all for today, and I thank you for your attention.